All right, so part two, picking up, we're going to get this function integrated now. And I, I caught myself here. I mentioned symmetry. You know, I said these are odd. These are odd functions. I don't know. I got caught up on this line y equals x. Inverses are symmetrical about y equals x, but odd functions are symmetrical. And that line is not y equals x. That's really weird. Odd functions are symmetrical with respect to the origin. You know, so with respect to the origin, these two pieces are symmetrical, which is great. So we can just simplify the work a little bit. Well, we are using symmetry. We're finding the area of this piece here and doubling. You could just as well go from from negative root 27 to 0 if you'd like. But you have to invert the order of these two terms. But in either case, we're finding the area from 0 to pi over 27. And again, we got this sine function on top. That's the red. And then we've got the blue function down below, which is the tan function. All right, so let's get, I'm almost not sure where to start in a way. Mentioned there's a lot going on. Now let's start with the tangent, because this is going to be something that I would encourage you to probably memorize, maybe from this point on, or maybe after you do it enough times, maybe it'll have it memorized. But I also want to see how tangent is done if you've never seen that before. So we're going to do the antiderivative of just simply tan real quick. Tan x with respect to x, and it is a u. So u substitution would be, you may be able to do it by parts or something, but simple u substitution. If we write tangent as sine x over cosine x, then we can do it as a u substitution. Right now, I don't want to call sine u because the derivative of sine is not 1 over cosine, but I would like to call cosine u because the derivative of cosine is negative sine, and that'll be helpful. Right? So we can say du is negative sine x dx. In which case, if we go to replace this now with our substitution, let's say cosine we called u, and dx, sine dx is just simply negative du. So we'll put negative 1 du. Right? Negative du is equal to the sine dx that we need. And now integrating this with respect to u, we've got the natural log of the absolute value of u, which remember u was cosine x, cos x, and then plus c. So this is the antiderivative of tangent with respect to x. It's the negative natural log of cosine x. So it's nice to have that maybe memorized, so we don't, every time you encounter tangent, we don't have to go through the substitution, but that is how you do it. So we're going to need that. So we'll come back to that. And then, outside of this little quirky thing with tangent, the way we're going to handle the substitution otherwise is going to be the same between the two of these terms, and that's the kind of thing that you'll probably figure out. We're going to integrate terms like these so commonly that you'll just have them memorized. You won't need to go through the substitution. But ultimately, when it comes to working with these trig functions here, where you've got like a linear argument like this, 9x, you're really just going to end up dividing out that coefficient 9. But to show you, I'm going to do it both times, because like I said, this is a good problem to practice a lot of trig and integration with trig. So let's start with, we'll integrate, I'm going to get rid of that. Well, let's do these separately. You wouldn't normally necessarily have to do these separately, but let's do them one by one. I'm going to start off with let's do the, I got this 2 here. Tell you what, I'm even going to distribute the 2 in for now. So when we go ahead and integrate this first term, we're working with 4, right? And then we've got sine 9x dx, right? All right. So we do have to do a substitution here. In particular, substitutions can be tricky because when you substitute, if you don't put everything back in terms of x, you're going to have to change your limits of integration as well. Some people like to change them, some people don't. Maybe I'll even take the time now to even show you that. So this is a good learning question. So let's say u is 9x, right? If u is 9x, then du is 9 dx. And let's see what happens if we go and replace what we have. So if I want to do the full substitution, right? If I don't want to have to worry about putting things back in terms of x, it's helpful to actually change my x values to u's in terms of the limits of integration, right? And notice if x is 0, u is going to be 0. So I can actually leave that 0 alone. If x is pi over 27, right, that's 9 times pi over 27, well then u is pi over 3. again, if x, this being an x value, is pi over 27, then u, which is just 9 times that value, is going to be pi over 3. Okay, and then we can just simply call this now sine u. And then notice the dx piece is actually 1/9 of du. So that's what I was saying. We're going to always end up dividing out that linear piece, the coefficient of that linear argument 9. So I've got, let's see, 4, and we've got to divide by 9. So I've got a 4/9 here. This is 1/9 du. And then you can just simply say, okay, well, this is the antiderivative of sine is negative cosine u. And remember, these are now u values. So I don't need to replace anything. If you did not change your limits, then you're going to have to make sure to remember to replace u with 9x. And then then you can use the old limits of integration. But remember, I changed these already. So these are actually u values now. So we want to go from, there's the 4/9 out front. We want to go from 0 to pi over 3. All right. So we've got pi over 3. Cosine of pi over 3. Remember, did I include the triangle? I didn't include my triangle. I'll draw it again. Remember my triangle? Pi over 3, pi over 6. And we've got, this is, let's see, root 3, 1, and 2. So the cosine of pi over 3, remember cosine puts the x over the r, or the adjacent over the hypotenuse. So cosine of pi over 3 is 1/2, but we've got a minus 1/2 here. So we got 4/9 times, this is minus 1/2. And then, remember the cosine of 0, everyone should know what the cosine of 0 is 1. So we've got minus, well, I got a minus, and then I've also got, there's a minus here, so minus 1. Okay. So, I don't know why I brightened it. Well, it doesn't matter. That should probably be parentheses, but either way, this will be our value for that first term at least. And remember, you won't necessarily do these. Maybe even at the end, I'll even show you how I would do this all at once, having seen it done. So this ends up being, let's see, minus 1/2, that's plus 1, it's positive 1/2. So we're talking 4/9 times 1/2 should be 2/9. Now remember, that's not the whole thing. That is just the sine piece, right? So we got the sine piece. We have to subtract out what we get when we work with tangent. Remember, and that 2 is common, so we're going to need to work with this 2 here. So I don't know if it's more or less confusing if I do it separately. But I am doing it separately now. And then again, ideally, get the hang of this substitution a little better. And, you can do this all as one integrand. You don't have to split it up. Okay, so I'm just going to make some room as best I can. Here's the sine piece. I should probably pause the video, huh? While I'm doing. All right, now let's get this tan piece integrated. All right, tangent is, and we already have our form for it. I probably erased it in my, that's okay. We know what it is, right? It's the negative value of natural log of cosine x. In this case, it won't be cosine x. It'll be cosine 9x, and we'll have to divide out the 9. So but let me show you. So we've got 2. And remember, we're again going from 0, at least for now, from 0. Oh, you know what? Let's change colors. Let's change colors. I've already got the sign in red and this in purple. Back to purple. Like purple. Okay, so pi, 2 from 0 to pi over 27. And then let's figure out what, remember, we're going to end up subtracting it. Let's just do the tan 9x dx. Okay. So, another u substitution, right? U is going to be 9x, which makes du equal to 9 dx, or I can say that 1/9 du is dx. And then we can call this tangent u. But again, I like to change the limits, right? If you don't want to do this part, then remember you got to replace all instances of u with 9x at the end. I would recommend maybe if you haven't done this process before, changing the limits, that you maybe embrace that a little bit, because there are areas in this class, not too many, but we're going to have to do a substitute. We're going to have like 2 or 3, I can't imagine any more than 3, but potentially 3, 3, upwards of 3 substitutions. I mean, at least 3 and if you start going from variable to, it's easy to get lost with these values. So I would encourage you to change your limits of integration along with the variables that you're substituting. So let's see, u is 9x, right? So let's go to substitute now. I've got 2, and when x is 0, u is still going to be 0, right? U is 9x's, so if x is 0, then u is 0. And again, if u is 9x, then 9 pi over 27, there's an x value, right? Pi over 27 times that 9 is another pi over 3. And now we can say, okay, well, this is really just tan u, and dx was our 1/9 du. So I'll put that 2 over 9, and we'll call this du. And then remember from the previous video, I showed us tan. I forget where I did it. I guess it was in part 1, or maybe it was earlier on in this video here, and I erased it when I paused. The antiderivative of tangent is that negative natural log cosine, in this case it'll be cosine u, right? We don't need a plus c, but that's the antiderivative. And we've got to go from 0 to pi over 3, and we're going to multiply it by 2/9. All right, so let's see. We've got 2/9 times, so pi over 3. We already said that cosine of pi over 3 was a half, right? It was a half. Where's my half go? Minus natural log of a half. Okay. And then we subtract, and we'll get, evaluating at 0, remember cosine of 0 is 1, so this is minus, but if you remember, well, we have to subtract this, so double negative is going to be a positive. This will be the natural log of 1, right? Cosine of 0 is 1. Well, the natural log of 1, if you remember, is 0. So it turns out it doesn't really matter if it's plus or minus. It's just going to be a 0 there, so I'll get rid of the 0. Which means this whole thing is equal to negative 2/9 natural logs of a half. Now, if you remember, this is the value we got when we just integrated simply that tan piece, right? And I did take out the 2, okay. We have to subtract it, right? It really was being subtracted. So it turns out, when we go to subtract these two values, right, when I did the sign, we got 2/9. So this should be equal to 2/9, and then minus, what we found was minus 2/9 natural log of a half. So it's really just going to be a plus, right? Minus, I'm going to take care of that now. It's a plus, I forgot it already, 2/9 natural logs of a half. 2/9 natural log, I don't need the absolute value, it's just a half, right? Natural log of 0.5. Should be fine. And that should be the answer. Now, yeah, we already took care of the 2, so that actually should be the answer. Let's see if we can, just to give you, since I got a little bit more time here, I got a 15-minute time limit, just to show you how you could check this work, right? Sorry, I just paused the video so I could skip. You guys don't want to watch me type this stuff into the calculator. But, you know, to check your work here, you just type the exact expression that you got in, and your calculator will give you a decimal approximate. And then when you type the integral into, you know, the math module that's in there, the math 9, the function integrate module, its decimal approximate should match, right? So it's a good way to check your work. Now, if this question's asking for an exact answer, turns out it didn't actually check, then you're going to need to do it by hand. And in either case, it's nice to see it done by hand. Like I said, tangent in particular is a nice one to see. That way, you know, you can see what it takes to get there, and then just maybe have that memorized, the natural log of cosine. With the negative up front. And then, of course, the substitution here with these linear arguments of your trig function. So, great question to ask, difficult question. Certainly not a test question, but I'm glad it was asked to me because, like I said, we went through a lot of pieces that really can kind of give you a taste of the type of working knowledge you want to have with algebra and with trig functions and things to work with some of the problems in this class. Okay, so thank you, and I apologize for the long video. This is now part 2, but take care, and I'll see you guys soon. Bye.